Hi everyone. For day 3, we're going to look at some properties of angles which are formed inside and on a circle. The first one is that angle formed by two chords that intersect within a circle is measured by 1/2 of the sum of the intercepted arcs. Now we have seen a result where we know something about the arc ratios, whereas in this case, what it is telling us is that this angle EPT is 1/2 the arc length CF plus the arc length DE. Now again, remember, these make sense because angles are being measured in radians too, and the radian measure we've seen corresponds to lengths on the circle. Second one, which is really important and helpful, as we'll see in an example later, is that an inscribed angle is 1/2 its intercepted arc. So whatever this angle here is, it's going to be 1/2 of the length from A to C. The third one says that the angle formed by a tangent and a chord at the tangent point is measured by 1/2 its intercepted arc. Now remember, it's only 90 degrees with the center. What about any other chord? For any other chord, the angle CAB is half the measure of AEB. That's where it cuts. Bonus here. This is third bonus question. Using this, show that tangent makes 90 degrees with radius. Okay, you can use this relation to find that. Application. Here's a cool application. How do you determine the center of a disk if all you have is a carpenter square? You basically have a way or a means to have 90 degrees. So here's what you do. You take the square and you place it somewhere on the circle. Okay, when you place it somewhere on the circle, that's going to be 90 degrees. You mark out these points, let's call them A, B, and then you join it. Now you place your square somewhere else. Let's say I place it here. This is 90 degrees. And I mark out these points C and D. And I connect them. This, where they meet, is going to be the center. The reason that works is we've seen that inscribed angle is related to the arc length. So if this is 90 degrees, then the arc AB is going to be half the circle, which means half of circle, which further means that AB is a diameter. Similarly, CD comes out to be a diameter as well. And the point where two diameters intersect, that's the center of a circle. Another example, you're given the lengths of arc CB, arc DB, and angle ECB. Sorry, this angle. And you're asked to find angle ADC and angle 1 and 2. Yeah, I forgot to label angle 1 and 2. So let's scratch that. Let's just try to find angle ADC. Okay, so what do we have here? We have CB. And we have DB. Okay, now because there's a chord here, DB, and we have this particular length, we can find this bigger angle right here. Say angle 1. Angle 1 is just going to equal the DB chord length, which is 168 degrees 32 minutes and 18 seconds. Now, how does that work? Is remember this right up here, which says if you have a chord, inscribed angle is 1/2 its intercepted arc. So over here, angle 1 is inscribed by dB. So it's going to be half the intercepted arc. So it's going to be half of that, which is going to be 84 minutes or 84 degrees, 16 minutes and 9 seconds. So that gives me angle 1. But I know angle ECB is 72 degrees, 8 minutes and 22 seconds. So I can find angle, let's call it ECD, as angle angle 1 minus angle ECB, which will give me this small angle here. Okay. Now if I have this small angle here, I can use that to find angle ADC, because that's our end goal. Okay, I think I'm missing some information in this problem. So for now, you can skip this, and I will post something related to this problem later. Okay, in the next video, we're going to look at angles outside a circle.